Section 5.1, we are going to focus in, as you can see by the title, on exponents. Now certainly we've already been using exponents in some basic order of operations things that we've done, but now we're going to extend this a little bit more. We're going to talk about some additional rules in dealing with exponents. And we're also going to talk about, and I'm going to actually start with an example with this and probably end with one as well in the section, of applying exponent rules to units or labels. So first of all, no doubt, we all have already been talking about the basic definition of working with an exponent. So if I have just, a simple example here, like 2 to the 4th power, let's say, we all know that that means multiplying 2 by itself 4 times. It's not 2 times 4. So in this case, we would end up with 16. So we know that kind of basic idea of an exponent. So let's kind of take a look at something here and talk about the relationship and how we can use exponents to think about units or labels when we're talking about things like a length or an area or a volume. So suppose we were to talk about the length kind of going across this, I have these squares here, but the length we would add up, we can visually see here, is 4 units. So just kind of start with that basic example. The length there is 4 units. So now let's take a look at, again, units is the generic term, whether it was centimeters or inches or whatever it was. So we're just talking about, that is really our label here. We're talking about 4 units on all of these. So again, from problem to problem, that label on the units might vary, but that's just kind of our generic term there. Okay, area then, so we know basic formula for area is going to be length times width. And so if I look at each side here, and it's already labeled there, so we have 4 units, and then on the other side, in this case it's a square, so side squared would have been okay as well. But we have 4 units times 4 units. Now what I want you to think about is almost a thinking of the units as one variable. So let's say I reordered this and I thought of this as 4 times units times units. And that reveals to me that I end up with 4 squared, of course, or 16. And just like 4 times 4 is 4 squared, units times units is units squared. So I end up with, in this case, 16 square units. So what I want you to make the observation about here is that area is a square measurement, a square units on its label, whereas length was just regular old units. All right, so let's end on this sequence of examples with volume. So we know that volume is length times width times height. So kind of just the multiplying of those 3 dimensions, which again, in this case, each of them happen to be, it's a nice little perfect cube there. They're each 4 units. So once again, I want you to think about kind of reordering this and think of it as 4 times 4 times 4 times units times units times units. And so that reveals that we end up just like 4 times itself 3 times is 4 cubed, units times itself is equal to cubic units. So if we're talking about a volume measurement, then that is going to mean that we have volume as a cubic units on its label. So we multiply labels just like we do variables. So there's a direct application of working with just that basic rule, kind of the definition of an exponent there, and we'll return to more of that at the end of this section. So let's do a few, what I guess I'll call warm-up examples. Things that we've already talked about before, just reviewing and touching on some important concepts here, things to keep in mind. So suppose I had 3 times 2 to the 4th. So one thing I want you to remember, order of operations. Don't get in a hurry and think, oh, left to right, that's going to be 6 to the fourth. You know, the exponent only applies to the number, the base that is right below it, taking care of that exponent. 2 to the fourth here, that's what we take care of as the 16. And then we just kind of think of this 3 is what we're going to multiply after we evaluate that exponent. So the 3 times the 16 then, of course, gives us the 48. Okay, so don't just quickly go left to right and get in a hurry and go out of order of operations. So that's something I've seen students do from time to time. All right, so here's the other biggie, and we've talked about this a lot as well. So just like in this first example, the 4, that exponent, was only applying to the base of the 2, and we knew that because there was no parentheses around the 3 and the 2, so it only applied to the 2. Exact same logic here. This exponent, in this case the 2, is only applying to the base of the 4 because there are no exponents. So this is 16, and again, this negative is just out in front getting carried along in a very similar way that the 3 was in the example number 1. So this one is negative 16. So we get our negative 16 on that. So that's a common mistake. A lot of times students mistakenly think that that means negative 4 times negative 4, and that's not what that means. If we intended to include anything more than just that base, that number right below it, then there needed to have been parentheses. So as is the case in this example, this now indicates taking the entire negative 2 times itself 4 times. So this is now saying the 4 applies to whatever's in the parentheses. So negative raised to an even power, or go through it one step at a time, but a negative to an even power is always positive, and 2 to the fourth, 2 times itself 4 times, comes out to be 16. Or just one step at a time. Negative 2 times negative 2 is 4, times negative 2 is negative 8, times negative 2 is 16. You can always just take it one step at a time as well. All right, so let's look at a couple of examples in reverse. So let's write the following expressions with an exponent, and let me kind of be specific, an exponent that's not just equal to 1, because you could take anything I give you and just call it to the first power. Okay, so just kind of thinking, and if we were in a classroom setting, these would be the kinds of things that I would give you. Both of these sets of opening examples I'd probably just put up on the board, these 6 examples, and I'd just walk around and then we'd share answers. So feel free to pause the video and give them a whirl on your own. All right, so looking at this, thinking about, what would we do? I might run through examples in my head like 2 times 2, is 4 times 2 is 8, times 2 is 16, times 2 is 32. Well, that doesn't get me to 27. So then maybe I just experiment with 3s, and I think about how, in this case, if I was to do 3 to the third, 3 times 3, let's do a little check here, 3 times 3 times 3 would be 9 times 3, and of course that is equal to 27. So it's just maybe a little bit of trial and error. Some of you would get them really quickly. I think number 2 is one that folks would get pretty quickly. They see that the 25 is the 5 squared, and then just kind of comparing it with the example up above, that number 2, remember, if you want to not include the negative in that squaring, then there's no parentheses, so just negative 5 squared. Or the only other way you could write something like that is if you were to put parentheses just around the 5. I've seen a lot of students do that from time to time in class, and that's okay. All right, last example here. There's a number of ways, because this one was real ambiguous. It just says write with an exponent. So I think the first thing I typically see from students, which would satisfy these directions, is just thinking of the 81 as 9 squared. Now, I want you to make an observation that would also be equivalent to taking the whole fraction 1/9 quantity squared. So again, if we were to kind of check that, think about how 1/9 the whole fraction squared is 1/9 times itself. And when we multiply fractions, we just multiply numerators and multiply denominators. So either of these kind of satisfies the directions here. And there's actually another one. If we were thinking about what we did with number 1, if we go to one more power, 3 times 3 times 3 was 27, times another 3 is 81. So we could kind of do the same thing with those two choices. We could say 1 over 3 to the 4th, or we could say 1/3 to the 4th power. Okay, so just kind of some warm-ups here, getting used to thinking just a little bit more, maybe deeper about some of our exponents, but nothing new there. Okay, let's take a look at one more example before we hit some of these exponent rules. So let's look at an evaluate problem. So we've done a lot of these, so kind of all review thus far. So negative x squared plus 2y squared minus z squared. All right, so remember, when we evaluate in algebra, we always are evaluating, or we're substituting into implied parentheses. And that's important here, especially as I'm thinking about, what is or is not being raised to these powers. And actually on the 2 in the center, the 2y term, let's make that 2y to the 3rd. I misread my own writing. Otherwise, they're all to the 2nd power. That's kind of boring. So that second term again is to the 3rd power. All right, so that's how we want to think about our evaluating here, and just paying a lot of attention about how this, especially on the first term, here's the most common mistake, is that first term, this negative was not part of that squaring. It's just out in front getting carried along. So now let's sub in the specified values for the variable. 5 goes in for x, -1 goes in for y, and 2 goes in for the z. All right, so let's get to our order of operations here. So again, in this first term, the only thing being squared is the 5. The negative is just out in front getting carried along. So our first term here is -25. On the second term, it is the -1 that is being cubed. Hopefully you remember a negative to an even power is positive, and a negative to an odd power is negative. So -1 times -1 would be 1, times another -1 would be -1. And then of course on the last term here, it's only the 2 that's being squared, so -4. So then just doing that little multiplication in that second term, that's really now -2. And then we're adding up 3 negative numbers. They're all negative, same sign, take the sum of all of them, that would be 31. And then in this case, -31 on that. All right, so there's our kind of warm-ups. When we come back next time, we're going to look at some exponent rules.